Welcome to my channel. This is Statistics 101, where we learn statistics in under 10 minutes. In today's episode, we are learning about continuous random variables. So let's start right away. So why do we need continuous random variables in the first place? Suppose it's a stormy day and you observe flashes. You observe one and you ask yourself, what's the probability that a flash will be seen during the next 10 minutes? In this case, our continuous random variable is the time itself, and the event of interest is the flash. Usually, continuous variables are measurable, like temperature or height or IQ or time, as in this case. So, continuous random variables are really interesting. So let's learn a little bit about them. So let's start with the definition of a continuous random variable. A random variable is continuous if its support Rx is not countable, and second, there exists a function that maps real numbers onto the interval 0 to infinity, where infinity is excluded. This function is called probability density function, or PDF for short. This PDF can be evaluated on any interval from a to b that is a subset of the real numbers and will evaluate. We can compute it by taking the integral of the PDF from a to b. A PDF has also the following characteristics. First, f of x is greater or larger than 0 for any x that is an element of the real numbers. And the second property is that the integral from minus infinity to infinity of the PDF is equal to 1. The first property makes sense since a negative probability density function would correspond to a negative probability in that interval, which obviously violates Kolmogorow's axioms. The second property makes sense since the probability has to be equal to 1 when we take the whole support of a continuous random variable into account. Note that the PDF itself can be larger than 1, but since we take the integral of the PDF, the area will have a larger height but a narrower width, and this will still lower the larger value of the height. So in total, we will not exceed the 1. And if you think a second about the definition of a PDF, you will notice that if you try to compute the probability for any given interval that has the same starting boundary and ending boundary, the probability will be 0. But how can this probability be 0? And this is where you have to wrap your head around. That is that a PDF represents densities, and this is the same as in physics. When you got a density and you want to compute the mass, then you have to know the volume. Because mass is equal to density times the volume. If the volume is 0, then the mass will be equal to 0 too, no matter how large the density itself is. That does not mean that an object with given density has 0 mass. It just means that the mass of an object depends on the volume of the object for a given density. With PDFs, it is the same. The probability depends on an interval of our PDF. If this interval is 0, this doesn't mean that an event will never occur, that it is impossible to occur at this given point on our PDF. It is not impossible, but instead we should ask what is the probability for an event to occur for a given interval of our PDF. Each point on our PDF has an area with width of 0. But the sum of those 0 widths areas are not actually 0. This sounds kinda crazy, but it is how it is. If you want to understand why this is the case, you will need to have a look at measure theory. But for simplicity, think about PDFs as density values as we discussed in the physics example. Let's do a mathematical example. So, what do we got here? We got an exponential function that is equal to lambda times e to the power of minus lambda times x, if x is greater or equal to 0, and 0 otherwise. And lambda is a parameter that is larger than 0. As a quick note, exponential distributions are often used when the amount of time until some specific event happens matters, like in the example that I made as an introduction with the flashes. So let's say lambda is equal to 1/2, and we want to know the probability that x will lie in the interval from -2 to 2. This probability can be split into two sums, one going from -2 to 0 and one from 0 to 2. The first term is 0, since our distribution is 0 for x smaller than 0 by definition. The second term can be evaluated quite easily. When we integrate the second term, we get minus e to the power of -1/2 x, evaluated at 2 and 0, and then we take the difference. This is equal to 1 minus 1 over e, so the Euler number, which is approximately 0.63 in total. That's how you can evaluate probabilities when having a PDF. You just have to compute the integral. In this example, x is a continuous random variable that can take any value in the interval 0 to infinity. The support is Rx. And we could ask, is this function that we defined a valid PDF? So let's see. The first property is fulfilled, since the exponential part is definitely greater than 0, due to the property of the exponential function. And lambda is also greater than 0. That was our assumption. So the product of both is also greater than 0. So that's correct. The second one is also fulfilled, since when we integrate our function from -infinity to infinity, we can again split the integral into two parts. One term is again 0, and the other one is evaluating our PDF from 0 to infinity. This evaluates to -e to the power of minus lambda times x, evaluated at infinity and 0. So the expression evaluated at infinity gives us 0, and the expression evaluated at 0 gives us 1. So in total we get a 1. So the second property is indeed fulfilled. So these both properties are fulfilled, so we are really dealing with a PDF. So that's it for this episode. Hope you liked it. If you got questions, post them in the comment section down below, and see you then.